Good morning, good afternoon, or good evening, depending on where you're joining us from. I'm Shweta, Business Development Executive from API Engineering. I extend a warm welcome to each one of you. It's truly an honor to host such a diverse and international audience, and we are grateful that you have taken the time to be with us today. This webinar is a wonderful opportunity for all of us to connect, share ideas, and gain valuable insight. And it's your presence and participation that make it all more meaningful. To ensure a smooth experience, all participants' microphones will remain muted during the presentation, except for the speaker. At the end of the webinar, we will have a dedicated Q&A session, during which you can unmute yourself to ask questions. Alternatively, you are welcome to type your queries in the chat window or send them via email mentioned here. Today's session will focus on the topic reverse engineering, bridging physical products and digital design. With that, I would like to hand over to Muthu, who is our head of engineering, will share a brief introduction about APA and present today's speaker.
So thank you, Sweta. A warm greetings to everyone. API Engineering is a 25-year-old organization, 500 people plus, headquartered in India, serving clients across USA, Canada, Germany, Netherlands, and Australia. We are ISO 9001 certified for the quality management and ISO 27001 and TSAC certified for the information security. These certifications help us in delivering high quality services, ensuring very strict adherence to global data security standards, thus giving a lot of peace of mind to our clients. Our services can be categorized into 4 divisions: engineering, sourcing, compliance, and technology. Sourcing team helps our clients to identify the right supplier for manufacturing needs and conduct quality audits during various stages of manufacturing, do pre-dispatch inspection, optimize logistic cost, and ship and deliver products at the client's doorstep. We'll cover about engineering in the next slide. Compliance team offer software products and services to clients, helping them to comply to various product chemical compliance requirements such as conflict minerals, IMDS, REACH, RoHS, Prop 65, etc. Our technology team is into providing software products and services to improve the enterprise productivity through smart custom-built IT products and services. Moving on to the engineering, next slide. So engineering division is a 70-member team comprising of mechanical, electrical, electronics engineers. Our service offerings can be classified into 5 verticals, such as product engineering, manufacturing engineering, embedded, digital modeling, and plant engineering. In the interest of time and today's audience, we would go over product engineering and manufacturing engineering services a bit in detail. With our knowledge in design and manufacturing, we create 3D models and prepare manufacturing prints with well-known details, machining details, provide GD&D information as per either ASME, DIN, or ISO standards. Oftentimes, we work in engineering change orders or design completion, where the client provides the concepts for us to finish the design. If the requirements demand, we also have the capability to design from the concept levels. We have a reverse engineering lab, having a hexagon portable CMM, which can do the scanning, probing of the physical components and assemblies to generate a profile in the form of a cloud point data, and then use a conventional software like SolidWorks to create the 3D models and prints. We validate the design by performing FEA simulations to predict performances such as strength, stiffness, fatigue, vibration, and impact responses. We also have the capability to perform thermal and flow simulations. We work on standardization of design variants that our clients might have, weight optimization using either topology or size optimization techniques, some of the material conversions like iron to aluminum or even sheet metal to injection plastic mold conversions, etc. Moving on to the manufacturing engineering space, based on the customer's requirement, we work on 5M resources optimization, which is nothing but man-machine methods, materials, and measurements. We provide solutions to improve the efficiency of utilization. This is often supported by performing FMBA studies, Part of this goes into layout optimization, line balancing to reduce the throughput time, and it's sometimes we have to do a design and redesign of the existing fixtures, your tooling, gauging systems to improve either the efficiency or process capability. And we also have CNC programming capabilities to improve the setup time, tool life, and operating time, and thus minimizing the downtime. We can also do PPAP documentation. You could see that we could provide services in automotive, oil and gas, SPM, some medical equipments, and in plant engineering fields. We work with companies of different domains, and so in varying in size from a single person company to a very large organization. Now moving on to today's speaker, Naveen Jayakrishnan. Could move on to the next slide. He is a SolidWorks certified design professional with an engineering degree in mechanical with 15 years of experience in industry. He heads our reverse engineering vertical. Over the years, he has executed and managed several reverse engineering of castings, forgings, plastics, and sheet metal components in an automotive and medical equipment domains, helping our clients to have the design data for the parts which they would want to outsource for manufacturing. So Naveen, would you like to take over from here?
Thank you, Madhu, for that wonderful introduction. Good morning to all who has taken time to attend this session. So today we are going to see and learn about reverse engineering and how it can help you and your organization in getting your products to market with ease. So in today's session, we are going to cover first, understand what reverse engineering is and why it is important. Next, we'll see what all industries this is applicable and generic steps involved in reverse engineering. And then we'll discuss about various tools and softwares we use for reverse engineering. And then we'll have a look into a video where we show you a demo of how reverse engineering is executed. And then we'll go through some common challenges which we face during reverse engineering and how we overcome them. And finally, we'll have our question answer session where you can raise your queries. So reverse engineering is the process of analyzing a component to understand its design, functionality, the material being used, and the manufacturing process associated with it. So basically, it involves taking apart and scanning the components to extract information from it. Now, why this is important is for various reasons. One is design recreation. So some of the components which are being used in the market could be, very old. For example, you take a vintage car. None of the parts are being produced now. So if you want to make something like that, then you use the existing part, you reverse engineer it to make new models and prints for it. Second is competitive analysis, which is nothing but benchmarking. So you have your competitor product, you want to understand the features and the functionality behind it, and you might want to incorporate some of the design and better it. So this is another reason why we can use reverse engineering. Next is to improve your quality. So let's say one of your component has some failures. You want to understand what the failure is and why it is occurring. So again, you can just use the component, reverse engineer, run whatever FEA is applicable for it, and you'll have your results. Next is for cost reduction. So reverse engineering can also help, getting the CAD data, which is later used for understanding which alternate material can be used or where material can be reduced to save cost, or how it can help in reducing your manufacturing or tooling operations. And the last but not the least is basic documentation. So you want to have some prints for your physical component. That's where reverse engineering comes into play. Some of the industries where reverse engineering is exclusively used is in automotive, aerospace, electronics, manufacturing, and medical devices. So apart from medical devices, the predominantly in all the other industries, reverse engineering is used basically for benchmarking, and like mentioned earlier, some old service components, like vintage cars, or let's take even an aircraft, for example. Aircrafts, are up in the air for, like they're being used for 10 years, 15 years, 20 years. So some of the components when it comes to servicing, you may not have the prints, or, that company no longer exists. So you need to find another supplier. So that's where the component helps in, or reverse engineering helps in creating CAD models and drawings for that particular component. And manufacturing, it also helps in, creating the tool, die, and fixtures for the components. And in medical devices, it is being used for creating implants and prosthetics. So, some person has, some scar on his face or the ear, you want to replicate, create a new one, you can scan his face. It's not harmful at all. So the scanner is used to scan his face or any other body part, and it's not harmful to him. And the 3D model is then goes into for 3D printing, and that's how it helps in medical devices. So the typical, let's have a look at the typical steps involved in reverse engineering. The first and foremost step is to scan the physical part. And so once the scan is complete, next is pre-processing, where you clean all unnecessary data, you extract curves, and you export them to any other software which you require for 3D modeling. So, and the next step is parametric modeling. So here it is a feature-driven 3D modeling approach where the model is editable. So you can use it for various applications. You want to add a feature, you want to remove it, or you want to change the design, you want to improve it aesthetically. So this parametric model helps you in achieving all those. And next, the parametric model goes in for a quality check, where the 3D model and the scan data is overlaid to produce hotspots or heat zones, where green tends to show that you have matched most of the places, and more red you see, the more mismatches there. So it again helps you to go back and correct the 3D model before submitting the final one. And of course, this model is then used to create 2D drawings, where the drawings can call out material data and all other parameters required to produce a manufacturing drawing. So let's have a look into some of the tools and softwares that are used for reverse engineering. Traditional measuring instruments involve vernier calipers, screw gauge, micrometers. But the limitations on this is that you can it depends on the geometry of the component. So it's limited to very simple geometry and very minimum dimensions. So nowadays we use the CMMs and the 3D scanners, and especially these 3D scanners, you have handheld ones, you have portable ones, they vary across various sizes, small to large, where even a small component can be measured, and up to scanning an entire manufacturing unit. So the application is very vast. And some of the reverse engineering softwares we use is Geomagic Design and also Polyworks. And for parametric modeling, we use software such as SolidWorks, CATIA, Autodesk Products, Creo. So any application or any software which the customer uses, the scan data can be aligned to that particular software. Now we shall have a small demo where we see how reverse engineering works. So in this case, we are actually scanning a brass valve. It has been cut into two halves so that the internal profile can be scanned. And the part is placed on a V block, and a glue gun is used to fix the part on the V block, since it's a brass component and it's not magnetic. So if it's a magnetic component, this step can be avoided. So after fixing the component, we create a clipping plane wherein, in this case, it is the top surface of the V block, so that when you scan, any data below the clipping plane will not be captured. So as we scan, you can see on the screen the cloud points that are being generated. So we make sure to capture all the data without leaving any gaps. So in this case, we would be scanning in two settings. So this is the first scan which you have seen. And then what we do is the surface which was in contact with the V block will not be scanned. So then what we do is, once this is completed, we flip the part, we go through the same process, and we scan the part once again. So once that is completed, we align both the parts, and we try to merge them with common points, edges, features, whatever is available for reference, so as to create one complete scan data. So once this data is ready, then you can see some edges which are protruding out. So next step is to clean all this data. It is very easy to clean all this, as you can use any other normal eraser. So it's as simple as that. So once the data is clear, what we do is we have to extract curves from this. So normally, based on the profile of the component, we have to extract based on the axis. So it can be an x-axis, y, or z. We need to ensure that all the features are covered in the planes. So we need to appropriately give the number of planes. So if the component is a very simple feature, does not have a lot of features in it, then what we do is we normally create bigger gaps between the planes, since it's going to be a continuous profile. But in the case like what we see over here in this valve, there is a lot of internal profiles. The contour keeps changing. So in such cases, we need to have more planes, so the distance between each plane is as minimum as possible. So once the curves are generated, the next step is to export them. So the curves will be saved as an STL file, and the scan data will be saved as an IGS file. So the next step is to import them in any software which you use. So in this case, we are going to work in SolidWorks. So as you can see, all the curves are imported in SolidWorks. And the next step is to use the curves, identify which curve you want to start with, create sketches, and then you work your way around to complete the 3D model. Yeah. So this completes the demo for reverse engineering. So next, we shall discuss about some of the challenges we normally face during reverse engineering, and we'll have a look at how we can overcome them. So one of the most common issue we see is getting a damaged part. So the part can be either cracked, it can be rusted, or worn out. So if it's not a brand new component, then this can create problems when you scan or measure the profile. So if there's a broken edge, then you may not get the right radius, or the right position, the measurement for that particular feature. The holes may be worn out, resulting in a bigger diameters. So in this cases, we first try to see if there's any symmetry in the component. So if there's a better edge or the better features in the other half, we can use that. Or we need to compare it to some similar components so that we can reconstruct whatever is damaged in this. Next is the fit and function. So sometimes the parts we receive may be a part of an assembly. So we are not sure what would be the mating dimensions of the profile of the mating component. So in such cases, when we receive the sample, the tolerance which is applied for making it is little difficult to identify. So, it could be in a maximum material condition or it could be in a minimum material condition. So in such cases, if uh, you know where this is being used, what is the application, if you have the details, then you can use your engineering judgment to do it. You can also do a 3D assembly simulation, or you can do a stack-up tolerancing to identify and confirm whether there is no interference or it's not a loose fit, or depending upon the application. Next is coming across complex geometries where there could be some internal profiles. Looking from outside, it could be a very straightforward, simple profile, but internally there could be multiple sections or multiple contours. So if you're not sure about that, the first step to do is maybe get a CT scan. And nowadays, CT scans are not used just for humans. It is also used to, identify if there is any internal profile for these components. So if you see that there is any internal profile, then to reverse engineer, we would have to cut the sample. Again, cutting the sample, if it's a symmetric profile, one half would do it. But if it's not symmetric, then based on the CT report, you would have to identify where all you would have to take sections to cut the sample. And next is coming across intellectual property. So, sometimes when you do reverse engineering on a competitor product, that particular component might have some IPs associated with this. And if you tend to use it, then you will end up in a lot of trouble. So what we do is, once we scan and create the 3D model, we need to also understand what the IP is about. And with the help of a subject matter expert, we will need to overcome by redesigning the features associated with the IP. And also, you need to get it validated before you can use it for your application. So that's pretty much about reverse engineering. So we went through the process behind it, where it is being used, and common challenges being faced in this. So now we are open to any questions if anybody has anything.
So thank you, Naveen. Thank you for sharing the valuable insight. So we have received a handful of questions. In the interest of time, we'll take a few questions to answer. Naveen, can you answer these questions? So
Yeah, sure.
yeah, can you provide manufacturing drawings?
Yes, definitely we can, but there is a catch to that. See, like I mentioned earlier, the sample we receive is already in either a maximum or minimum material condition. So if you want a detailed manufacturing print with all the tolerances applied, then we will definitely need a batch size of either 5 or 10 components, depending upon the complexity and criticality of the component. So so in this case, what we do is, either 5 or 10, the or n number of components, we scan each and every component, create a 3D model out of it, or 3D model also is not exactly necessary, but we can compare the scan data, uh, arrive at the dimension range. So what is the minimum and what is the maximum? And so that will help give us the mean value, and you can apply your tolerances suitably. So in that way, you can get a complete manufacturing drawing.
Okay. So the next question is scanning of transparent and highly glossy surface possible?
Yes, that is also possible. So you see, again, if you're using a regular CMM, then uh, the looks of the component is not of high importance. But if you're using a scanner, 3D scanner, then yes, this plays a big role in the outcome. So if it's a transparent surface, then we can use a spray paint so that the thickness of the component or the dimension doesn't change at all. You can use any black or any dark colored paint on it. And if it's a glossy surface, then we can use some white adhesive powders on it so that it does not reflect back the laser which is being pointed at the component.
Okay. So the last question is, what is the accuracy in which you can scan?
There is, okay, regarding accuracy, there is no one answer to that. So this depends upon the equipment which is being used for measurement and scanning, and it also depends upon the component which needs to be measured. Now, for example, you want to reverse engineer a piston, so a component like a piston requires high tolerance. So the appropriate device or measuring equipment has to be used, where the accuracy ranges from even 5 microns. And that is the equipment which has to be used for critical components. Now, let's say it is some plastic component. So plastic normally tends to bend and vary a lot. So in such cases, the tolerance is not of very high importance as compared to a piston. So you can use a device which has a more lenient tolerance, like a hexagon arm will have an accuracy range of 30 microns. So you can use equipments accordingly, and you'll get your output well and good.
Okay. Thank you, Naveen. Thank you for answering all the queries. So if we miss your questions, don't worry, we will make sure to follow up with you by email. So now I request Muthu to provide a vote of thanks for today's session.
Thanks, Sweta. So, on behalf of all of us at APA Engineering, a big thank you for joining today's webinar. We truly appreciate your time and interest, and we hope the session provided some valuable insights into reverse engineering. As we conclude, you will receive a short survey form. Kindly request you to take a moment to share your feedback, any questions, suggestions, or even a simple comment about your experience. This would help us a lot to improve as well as deliver more value in the future. Thank you so much once again.